We'll go ahead and get started. So this is going to be a one-on-one in time series analytics with Apache Arrow at Pandas and Parquet. So this talk, just for reference, is sometimes closer to an hour long. So what I've done here is I've organized a lot of extracurricular materials, I guess you could call them, that will take you through things like anomaly detection, forecasting. There are lots of examples, wonderful Jupyter notebooks, a lot of resources for you to take advantage of after this talk. So for right now, we're going to go in to some of the technologies, and pretty much everything I discuss here, by the way, will be available open source. So that's going to be the big focus, is open source, Apache supported projects, etc. So she said, my name is Zoe Steinkamp. I'm a developer advocate at Influx Data. You're welcome to add me on LinkedIn if you want to ask questions after. You know, if you don't want to ask it to a whole audience or you just want to follow and see what I'm up to, either way works. So the first thing for our agenda is we're going to go over why you store time series data into, for example, a time series database, some tools to know, what is Apache Parquet and Apache Arrow, an Apache Arrow example, and as I mentioned before, examples for you to take home. If we have the time, I'll go over one of the autocorrelation examples. We're just going to see where we land time-wise. So the first thing I want to ask the audience, though, so that way then I can kind of gauge how much I should talk about certain information here, is raise your hand if you've ever worked with time series data. Okay, so most of the audience. How many here have worked with a time series database with that data? Okay, a little bit less. That's about where it tends to fall. In case you're curious, you guys are average, you're normal. So why is a time series database important? So time series data tends to end up in three categories, and most people will know the first one, which is metrics. If you're ever talking to somebody and they have no idea what the hell you're talking about, I always talk about my Fitbit, or you can point to like your health tracker, your Apple Watch, etc. These are time series metrics garnered about you, and although when we go to the app, it shows us something that's extrapolated by the hour, like how many hours you slept tonight, or how long was your deep sleep, it's normally by the minutes. I can assure you, when it's actually tracking you, it is taking it by the second at the very bare minimum. It might even be by the millisecond, because your body changes quickly, and it's pretty normal to take about that amount of metrics data. So that obviously gets pretty large, which is a big key piece of time series data, is it tends to have what we call high ingestion load, or basically really noisy, is what we also tend to call it. IoT data is very noisy. The devices like to talk to you about a lot of stuff. They like to tell you things. The next one is events. So events are changes that are irregular, basically. So with this one, I tend to mention like a button on a website. You know, hopefully no one's just sitting there clicking the button every millisecond. That'd be a little strange. But basically, once in a while, somebody clicks on something or something happens. Normally, this especially is relevant to something breaking. Something goes wrong, and that is considered irregular, and it's an event. The third one is especially common in things like OpenTelemetry and just observability, which is traces. And a trace is basically a complete event or request that has a lot of metadata about it. Basically, it says, you clicked on the bucket, and we called for the shopping cart, we called for an outside provider, we called for a database, we made like 100 extra calls, and this is how long each one of those took. This is where an error possibly happened. That's what we call it, a trace stack. A trace is just a very long chain of information and events and metrics that have happened. So those tend to be the three main categories. So I always like to point out this slide because people tend to put their time series data just, normally it's wherever is convenient or something they're familiar with, but there can be difficulties in working with a non-time series database. So for relational, the biggest issue you see is the fact that a SQL database was not necessarily intended to receive 60 million data points a second. It wasn't really made for that high throughput, but it also wasn't made to query on time. If anyone here has ever worked with a relational DB, you query normally based off an ID. It's some kind of order ID or an ID of a person. It's some kind of identifier. And you can have secondary indexes as well, so something that would be like your secondary index is now time, but that's still a little bit weird because it's still going to look through pretty much all of the rows. Basically, the sorting algorithms for your SQL database were not meant for this. What they normally do is they take that ID, you know, they do like a merge sort tree, et cetera, till they find your value. Very great. But when it's dealing with time series, it was never meant to do that, so it can't do that quite as efficiently. So it's going to take a bit longer. And then when you query something like, give me the past data points for the past 60 minutes, and that is a return request of like 1 million data points, it also doesn't appreciate that either. So then you have something like MongoDB, which is a NoSQL database, which is certainly, I will say this, if you're going to use anything for time series data, a NoSQL database is normally a bit better because you can change the primary index, and because it's normally something that's like columnar stored, et cetera, it can normally handle that high throughput in particular, like it mentions here. The only thing is, again, it's not really made for querying on time, though Mongo does have a time series solution. but it's a little bit weird in that they don't focus on it very much for our data scientist. So they have it, but it's more about, it's more of like a checkbox, in my opinion, that they marked, and they were like, yes, we can do it, we can store the data. Though I will say I've talked to some MongoDB experts, and they certainly can do many magical things, but they have years of knowledge that not everyone gets to take advantage of. Then you have your search, which, to be fair, Elastic is very good at logs, which are also basically time series metrics. They're also very good at time series that is related to searching, unshockingly. But again, they can be a little difficult if you need something out of the box, basically a custom solution. So in our case, we tend to deal with a lot of industrial IoT-focused people, and they don't use something like Elastic because that's not going to work when you're dealing with random IoT devices on a manufacturing floor. That's not really what it was made for, which is where something like Influx Data comes in, or other time series-specific solutions. If you just look up time series database, you're going to find like 10 of us. We're actually not that big of a category, but there's at least 10 well-known, well-tested good ones. So this tends to be the architecture platform, and although it says InfluxDB 3.0, this tends to be how it is for pretty much all time series databases. A few options will have things like data visualization analysis built in, but most people use their own tooling. So you might use Power BI, Tableau, et cetera. For visualization, we always suggest people take advantage of Grafana. And then you have your data sources, and then basically the big thing is the database deals with things like the data collection, which I'm going to go into, and the data storage, which is really just, compression. For us, the ability to delete. That's another big thing that a lot of time series databases offer, is the ability to delete your old data, because a lot of people are real-time monitoring IoT devices, and basically when the real-time becomes not real-time anymore, it's 3 days later, they want it to go away. Obviously, that's a little weird because for most of us here who work in data science, that's not really how it works. How the heck are you going to do anomaly detection without historical data? But they also might want to condense it as well. So they might want to say, instead of by the nanosecond or even the second, can you please give me the average over the past minute, average over the past hour? That's what your health tracker does. It condenses that data down so the storage costs are much lower, which is why I don't have to pay for Fitbit Premium and I can still see my data like a year ago, because it doesn't cost that much to store once it's condensed down. So some tools to know. If there is anything you take away from this talk, it is that Telegraf, which is an open source ingestion agent for metrics, is amazing. That is the big thing to take away here. It is an awesome open source collection agent. It can put the data into something like Influx, but it can also put into things like Parquet files, other DBs. It has a bunch of, we call it output plugins, and then it has about 400 input plugins. It's simple to configure. It's basically a YAML file that you get set up, and it is absolutely amazing. Here are some of the categories of Telegraf plugins. So you can see some of these are very specific to, work, industrial IoT, the databases. So for example, the databases is getting data and metrics off of your database, like basically how healthy it is, how happy it is, et cetera. And then we also have I like to call them the fun, non-work related ones, like Minecraft. It's open source, so you can add whatever you want. So we do end up with, CSGO and Minecraft and a bunch of other more fun ones. And this is just a very small piece of this, by the way. This, like I said, there's over 400 of them. And we are basically the caretakers of Telegraf. So we do not produce every single one of these. We just make sure that, hopefully no one maliciously adds Telegraf plugins that are going to give you like malware or something. That's basically our big job. Most of these are supported by the companies that maintain them. Docker is supported by Docker, AWS is supported by AWS, et cetera. So they're also all kept up to date by that support. Because, again, a lot of these companies actually use it as well as a data sync. So you could, get your data from Google Cloud PubSub, and then you could store it in an AWS S3 bucket if that is your, poison, if you decide to, be disloyal, I guess you might say. So something else I wanted to mention is SQL aggregate functions. So this is something in particular that InfluxDB 3.0 can do, which is that we have a SQL query language. It is anyone who has a database being powered by the Apache Data Fusion query engine can do these. It's an engine specifically geared towards NoSQL, so no non-relational databases using a SQL query language, basically. So I could have a whole talk about how SQL versus NoSQL is a ridiculous way to name anything. But basically, non-relational databases that will query with a SQL language, and they include SQL aggregate functions, which obviously make data scientists and anyone doing data science and analysis very happy, because it's one less thing that you have to do in Pandas or anything like that. So I've already talked briefly about what Apache Data Fusion is, but let's talk really quick about Apache Parquet and Apache Arrow. So Apache Parquet is basically a way of storing data. It's open source. It's a column-oriented data file format, which basically means it is for NoSQL columnar databases. Sorry, guys, I have to think about how to do all these sentences. And it's pretty much just designed for a very efficient data storage and retrieval. Basically, it is the better CSV file. That's really what it's going for, so much so that this slide basically explains that as well. So you have your data stored as CSV files. You throw them on something like Amazon S3. It'll be about 1 terabyte of storage if it's in that CSV file. You can imagine it as anything. And then you store your data in something like Apache Parquet format. Now you're getting a much faster query runtime. You're getting way less actual storage, so that's going to save you a little bit of money. And then you're getting 99% less data scanned and 99.7 savings, which I am not guaranteeing those savings. I don't know how much it costs to store anything on S3, but I also think that they purposely made this so that would be a penny. So I think they purposely got it just right, so that would be the exact amount of savings you would have. But basically, it's very good for compression. So much so that this is a slide that one of my engineers gave me. Basically, our old version was a time series metrics database, and our new version, v3, is built with Parquet file format. And this is how much savings we ourselves saw when we started to store files. Well, technically, our customers saw the savings, but this is what we saw that we then determined that we were going to build upon this. And basically, Parquet saved us a bunch of money, it saves us a bunch of storage, and it's actually a little bit easier for us to also query through. So basically, it's very, very good for compression, which is important for a time series database because when you're benchmarking or you're trying to get customers or people to use your open source, compression is going to be a pretty big thing they're going to look at. Again, if you're storing billions of data points, millions, even millions of data points in a minute or something, it's going to get big real quick. Apache Arrow, though, is a framework for defining in-memory columnar data that every processing engine can use. So Apache Arrow powers basically a lot of data analytics tooling, and it powers a lot of databases. Basically, it's a language-agnostic standard for columnar memory. So the only caveat on that is you got to be able to read from a columnar memory format. It's very good for running large analytical workloads because it basically takes advantage of more modern CPU and GPU architectures, and it supports a pretty wide range of programming languages, including things like C++, Java, they don't matter, we care about Python, and R. So this is straight from the Apache Arrow website, just a heads up. This is you'll see it there, and it basically is explaining that it runs a lot better in particular on this one, an Intel CPU, but it's basically just because the way it's storing the data format, it works a lot better with modern equipment, basically. It's just much better for that single instruction, multiple data operations that our modern processors can handle a lot better. The actual project itself, I think, is about 5-ish years old. I'm not quite sure how long it sat in incubation, but it's fully fledged now. And then finally, you also have something called Apache Arrow Flight with SQL, which is pretty obvious that it just is a SQL interface for Arrow Flight. It involves being able to run SQL queries. So that's the other thing, too, is depending on where you're getting your data through this format, you can do it through something that does a SQL call or something that does, a non-SQL call that's custom built. So just to be clear here, one is query language agnostic. That would be Flight. It returns Arrow results. Flight SQL is basically a superset of the Flight API that's SQL specific. It's designed for ORMs and UI builders, implementation agnostic. For your purposes, and for the purposes of the people in this audience in general, for the most part, it doesn't really matter which one you're using. It matters more in just the fact that you have the ability to use both. So before, when you wanted to get things transferred, you had to have a lot more serialization and deserialization cost, but now with Arrow Flight, you can just basically send this data directly, and I really like this slide to show. So basically, before you would have to do a lot of copying and converting if you wanted to go between Apache Spark to Cassandra or Apache Apollo to Apache Drill. You just had to basically do a lot of copying, converting, very inefficient, a lot of deserialization, as it would be called. No longer. You don't have to do that anymore. You can go ahead and basically be able to access. So on this bottom row, by the way, all of those 4 databases you see there, Dremio, ClickHouse, DuckDB, and InfluxDB, are built with basically Apache Arrow, part of their core, I suppose you could say their core, their ecosystem. Most of the stuff at the top is your, actual data science tooling, or just in general the tooling you want to take advantage of, pandas, polars, et cetera. But they all have Apache Arrow capabilities, which allows you to be able to transfer your data from something like DuckDB into Apache Spark, and then you can also throw it into pandas, and et cetera, et cetera. Basically, it just makes the data flow a lot more efficient. So what InfluxDB does is, for example, we are built with Apache Arrow, Parquet file format, in Data Fusion, which is our SQL query engine. From there, we use that Apache Arrow to power our client libraries, which are basically just RESTful APIs that allow you to put the data in the database, query them back out, and then from that querying back out, you can send them onward to technologies and tools that either have Apache Arrow or, like, Grafana doesn't have it, but you can still use it for visualization. But Plotly, Apache Spark, those other ones do. And basically, we've also done it with the Flight SQL flavor of Apache Arrow because we have SQL capabilities. We also actually use the vanilla one as well for our own old language called InfluxQL, which is SQL-like, but not SQL enough to take advantage of the Flight SQL one. So basically, we actually use both versions for our client libraries. So let's really quick go into an example. So this is how you would create an Arrow table. So you have your table. It's pretty straightforward here. We're just creating a small table that has some animals, the count of those animals, and the year. And this one is from 2022 because we did this project back during the pandemic. That's when we were building out the client libraries. And so with that, for example, with this one, we're doing from Flight SQL, import the Flight SQL client. So this one, we are using the Flight SQL version. It depends on where you're getting your data out of, which one you would use. Plenty of people have the documentation for it. From there, we query against InfluxDB's Flight SQL endpoint. So again, we're basically just taking advantage of our Python client library to do a RESTful call where we're saying, select all from the IOX machine data, where the time interval is basically 1 day. Basically, give me all the data back for a day, and then go ahead and make a reader to consume the result because, again, this is going to be a ton of data. In theory, if it's machine data, it's going to be pretty big. And then go ahead and throw it all into a PyArrow table that I can read. So this is the resulting data frame. For this one, we've included 20 values with the head function, just to make sure that it also returns multiple time points for each sensor. Otherwise, we would just end up with like the same sensor ID at the top because of the way it would be queried in. But basically with this, you can see our CO2 levels, our humidity, the sensor ID associated with them, temperature, and a time. And you'll notice the timestamps are repeating, but that's because we have different sensors here. So that's basically how the data is stored and formatted. So Arrow comes built in with utility functions that makes it very easy to do things like, for example, what we just did, where you convert it to a Pandas data frame, and then you sort the values by something like time, and you give it a head of 20, so you only end up with a very short little data frame of 20 values. You can also actually load the data directly from a Parquet file, which is great if you need to do converting, you've got like some random files sitting in an S3 bucket, and you need to get them into something a little bit more easier to read from. You can just use Arrow utility functions to read from that Parquet file and send it onward to something more, helpful for you. But at the same time, maybe you do just want to save some random files. You can also do that. You can go ahead and save your table to a Parquet file and then, give it to your coworker via a sketchy USB drive. And then you can also do aggregation as well. So maybe you're using something that, unlike Influx, doesn't come with those awesome SQL aggregation functions. Not a big deal. PyArrow actually comes with its own aggregation, and although it's PyArrow in particular, I do believe the other language libraries also offer aggregation. But with this one, you can do things like grouping by, which would basically just say, give me all the machine IDs, aggregations like the mean, the max, the min, and then also converting it back out to pandas. So that's really helpful and really great because, again, this is specifically tooling that was definitely built with a analytics and data scientist mindset put in there. In general, it's also NoSQL data, so that tends to be data that's, again, going to be manipulated like this. The other thing that we're showing here that's really important is downsampling with pandas. So I actually mentioned this earlier when I was talking about how people like to be able to delete and make their data smaller for compression. This is how they do it. They do downsampling is what we tend to call it, which is basically this one saying, for every 10 minutes, give me the mean, and basically drop everything that's not that. So give me my sensor IDs, so sort the data by the sensor IDs, so sensor 1 and sensor 2 are together. In that 10 minutes, can you please resample on the time and give me the mean? So that will give us a much, much smaller amount of data to work with, so this is basically how it's going to look like in the end. So as you can see, for every 10 minutes, we're getting our means of the CO2, the humidity, and the temperature, and it's sorted up by that sensor ID. So with this data set, we had it for about, we're cutting it off, obviously, for the ability to actually be able to read this. But as you can see, it's basically every 10-minute chunk, and then you get your mean values right there. And with that downsample data, you could go ahead and store it or continue to use it for your analytics. Again, this is something that people really do try to take advantage of, especially when working with time series data, because you don't always need it down to the second, let's get honest. And IoT devices, You can't really tell them no. I don't know how many people here have ever worked with IoT devices in this room, but I have quite a few at home, and you can't tell them not to send you data every second. That's not really how it works. They're going to send it to you regardless, but you can decide what you do with the data. You have the power. You have the power to also downsample before, for example, you even store it somewhere. Save yourself the time, the money, and the heartache on that one as well. So with this example, we're also then just basically sending it back, for example, to InfluxDB. But again, you could send this onward to anyone who has an Apache Arrow. I'm going to just call it plugin, whatever you want to call it, but basically it has the ability to take this. And with this, we're just basically saying, I've got a token, I've got an org. These are just all things that basically are saying where I want to put it. And with us, you also have to say which timestamp column it is, because we're expecting a timestamp. That's a requirement, at least for our database. You have to give us a timestamp. And then we also allow you to have what we call tag columns, which are basically just your secondary index. It tends to be the thing that you're going to query upon the most often. So that's the ID or something like that tends to be your tag values. Everyone stores the data a little bit differently. So now this is what this looks like when you take it into a Plotly dashboard with, we've taken advantage of Pandas, we've taken advantage of Arrow, and basically you can start to see the vibration level of the machines. Now, really quick, in our human eyes, we can kind of make a guess where things maybe are anomalous, maybe they're not quite right. We can see gaps, I suppose you could say, like we can literally see some of them are smaller, some of them are bigger. But something that we want to take advantage of is the anomaly detection toolkit. So this is a really, really awesome open source library for anomaly detection for time series. It's kind of very quiet. It's on the DL. A lot of people who use this tend to be in industrial IoT settings, but we tend to use it quite a bit for our own purposes when we are displaying this, because it's really awesome and it's open source and it has like the most common 50 anomaly detection options. But with this one, you can actually see the little red dots, which again, this is kind of more obvious to us visually. We can see it. It's very obvious to us when something's not quite right, when there's anomalous data. But we don't want to trust the human eye. That's a lot to put on one person. And two, this is really great to take advantage of, to be able to easily recognize those anomalies. And obviously, the more historical data you give it, the better. So this is a library here. This is an example architecture where we have that machine data that's been aggregated. So with us, what we're doing here is we have a machine simulator, which is going through an MQTT broker, which is then going through a Telegraf MQTT input plugin. And in Telegraf, we send it up to this, I believe, is taking advantage of our open source. It sends it up to a data bucket. It aggregates that data down with a PyArrow script, and then it visualizes it in Grafana. So this one takes it a little bit further, I suppose you could say. It has a few different ways. It's like an adventure game. You can kind of do it as you desire. I think we have just enough time really quick to go over this autocorrelation example. So basically what autocorrelation, for those of you guys who don't know, it basically just refers to the degree of similarity between a given time series and a lagged version or historical version of itself over successive time intervals. In other words, it's basically just intended to measure the relationship between the present value that you have and the past values or historical data that you have access to, which is why I kind of mentioned that for data scientists, we don't really want to delete our old data, because how are you going to find autocorrelation if you don't have anything to reference? You're just making a random guess, which is also why, again, Anomaly Detection Toolkit is much more powerful the more historical data it has to look at. These are very long-winded examples. We're just going to kind of skip through this really quick. So what we did for one of our examples is we basically took the National Oceanic and Atmospheric Administration Center for Operational Oceanographic Products and Services. I really like saying that. That is a ridiculously long name. But basically what we're doing is we're looking at water level and water temperature of a random river in Santa Monica. And for this, we're just using the InfluxDB Python client library. A Jupyter notebook is also linked at the end of this for you to take advantage of. But basically, we've got this data set. We're going ahead and looking at it. And once we connect up to the client, we query the water temperature data, and we're going to plot it. So with this, the big query here to pay attention to is that we want the mean degrees as HGO temp from our database. And we also want to group by the time of 12 hours and limit it to 60 values. So what that will actually look like when it's graphed up is it will look like this. An ugly little graph. So from looking at this plot, it's not really apparent yet whether or not there's going to be any autocorrelation with this data. There's not really a presence of seasonality. It just looks, like I said, like a graph that's kind of going crazy. Clearly, the HGO temp is like all over the place all day. So right now, there's no obvious way of saying, like, yes, this is autocorrelation. But what we can go ahead and take advantage of is the pandas.series.autocorrelation. So this method will basically be computing what is called the Pearson correlation between the series and its shifted self. So what we're looking for here is if the values are very close to 0, that pretty much means there's no correlation. If they go to 1, there is normally very much correlation, and if they go to -1, there's a negative linear correlation. But basically for us, we are getting numbers that indicate there is no autocorrelation here. Basically the data, and we can also go ahead and plot this out as well with an autocorrelation plot, but we can see that they are also within what's called a 95% confidence interval, which you can kind of see by that solid gray line, which verifies that our data doesn't really have any correlation at all. So basically it doesn't matter what the water's levels are, the temperature is not correlated to those rising water levels, which probably just indicates that, that probably just indicates basically that there's no seasonality. This river in Santa Monica is not receiving water from like up a mountainside or something like that, or it's far enough down that basically the only thing that's affecting the temperature at this point is not really the water going up and down, but more just like the outside air. Basically, it just means that, it's not also correlated to historical. It doesn't matter if the water was cold yesterday, it has no effect on the water temperature today. So some resources and more tools to know. So this is the big one that I already was talking about, which is a Python package for rule-based anomaly detection, otherwise known as the Anomaly Detection Toolkit. It is geared towards industrial IoT use cases, but honestly, as long as you're down with, anomaly detection, you can take advantage of all of these. This is just a small screenshot of some of them. Like I said, I think there's like 30 or 40 on the full website. You have TensorFlow, which is for machine learning and artificial intelligence. So data scientists tend to use TensorFlow for building and training models using Python or JavaScript. For here, we have some resources for using TensorFlow with InfluxDB, and again, you can kind of take advantage of the Jupyter Notebook if you intend to use it with other data sources or just take it onward. You have Prophet, which is a Python library for forecasting. It especially is good for curve fitting exercises or creating mathematical models. It works, as my coworker told me, very similar to Holt-Winters or triple exponential smoothing, but basically it can combine things like seasonality, trends, and holidays. And this is resources for everything, just to make things a little bit easier for everyone. So basically with this, we have our autocorrelation blog. We have our autocorrelation notebook. We have a very nice article written by, I'm forgetting the name right now, but basically it's how not to use time series for forecasting pitfalls, basically avoiding some of the pitfalls with forecasting with time series data. Forecasting and anomaly detection examples. PyArrow docs, so you can take advantage of all the awesome PyArrow features. And seasonal ARIMA with Python, which is basically a extrapolation of the original project, and it's again like a good article to read to kind of just like see how this would look with some of the tools that are mentioned here as well. Basically, it was part of the inspiration for that original NOAA project, which I kind of cut short halfway because there was a few more slides about it, but again, this is one of those ones where you're just going to have to take it home and look at it later. Also, you can try it yourself if you want to take advantage of InfluxDB. Just to reference, that GitHub Influx community, that is where all of these notebooks live. So although you did just get like the exact URL, you can also just come here and look up, something like, I don't know if you looked up pandas, if it would come up, but some ability to say like anomaly or something like that, or forecasting, and these notebooks would come up and be available for you. And then obviously the Influx Data website is just a great place for more resources and more information around these kind of awesome technologies. So I'm going to go ahead and leave it here for people to, grab screenshots as they desire. And yes, we're pretty much just out of time. But if anybody has any questions, please feel free to ask.
This is specific for cloud provider time series. One of the challenges we are facing is when we send IoT data, it's hard to get all the data timestamp synchronized, because when you provision them, they send the data through different gateway to aggregate back to one locations. But there's a timestamp there's a latency difference between different gateway across the globe. So do you have any solution for that? What kind of resolution we can deal with today with a cloud provider in terms of accuracy on time?
So I think the gist of the question was you were asking about how to basically keep your time in the correct value, basically. So one thing that we do suggest, especially for our clients who deal with lower latency, like they have connectivity issues, is that you assign the timestamp when you first grab the data So for example, that's something that Telegraf does, is it will grab the data, it'll take the metric, it'll assign the timestamp of right now, it'll do the .now function basically, or you can actually tell it an old timestamp if you need to. And from there, it will basically store it in like a very small, we call it a dispatch queue basically, and it'll stream the data up with that correct timestamp. So yeah, if you're worried about something like lagging or converting your data between, the other thing to keep in mind is most people when they're pulling their data out, it's already got a timestamp. So they're not like putting a new timestamp on it per se, if that makes sense.
Hey, any more questions? We have a question over here.
Hello. Yeah, I want your recommendation on some beginner project for a developer to get the feedback in time series as well as everything that you've kind of like covered. A beginner project in the way that it's not really like a toy, but it's something that someone helped me realize how the time series database is used. Like you started with a very good example of a Fitbit, so that's the motivation for my question. Like any good beginner projects that uses time series?
Yeah, so I mean, when in one of, I believe it's in the forecasting and anomaly detection examples, we have a few small projects that you could look at, including that original one. The autocorrelation notebook has like the NOAA one, but this one has other ones with, again, like the machine vibration data, for example. But I honestly think the best thing to start with is a data set that you are, I hate to use this word, but passionate about or interested in actually using in some kind of data science context. And if it's time series, obviously that makes it a lot easier to take advantage. But you have like a time series data set. And when I say this, the reason I use passion is it doesn't have to be related to like a job. Like it could just be a data set that you're interested in, kind of like that ocean and atmospheric one that we took advantage of. And you can go ahead and start working on it and take some of the examples in these notebooks and start to put them into play. That's why we built out the notebooks, is to make it easy to basically do it on your own beginner data set or beginner project, or take advantage of these and build upon them.
So we're, unless we have, maybe we can take one more short question and then we'll head off to lunch. Anybody else? Oh, we've got one more. I don't really, wait a minute, wait for the mic.
No one's allowed to yell in this room.
I'm embarrassed to have the mic because it's a really stupid question. But I actually don't understand what Pi Arrow is. Is it just a format? Is it like a...
Yes, it's basically the Python Apache Arrow language, what's the word? Not project, but basically, yes, it's just basically the Python version of Apache Arrow and being able to use it with Python for the data format transfer. Sorry, I'm like, you're asking a very good question. I'm answering it very poorly. So it all worked out in the end.